Welcome back, everybody. We're going to work on a complex numbers review today out of section 1.3. A reminder about the imaginary unit I. I is equal to the square root of -1. And so if I were to square both sides, the square and the square root kind of cancel each other out there, which means I squared is equal to -1. I would make sure that these are note card worthy, even memorizing, because you have to know those. But definitely make sure they go on a note card. Complex numbers. Complex numbers have real and imaginary parts. So A is the real part, and B is the imaginary part. And that's because it's attached to the I. So if we have the square root of -A, what we can do is take that and rewrite it as the square root of A times the square root of -1. Because whenever the radicals are the same, I'm allowed to multiply them together. We know that the square root of -1 is I, so that I comes out. And then the square root of A, since we don't know what that is, would just stay the square root of A. Another thing to note is that I is always written last, except there's one exception if there's still a radical in your answer. So like this A one, because we still had a radical, only because we don't want to make it confusing to say the square root of A times I. Can you do it? Yes. But sometimes we're not sure, did you mean for that I to go under radical? Did you not mean for it to go under the radical? And so just putting it in front eliminates all of that question. So let's try this. 16. We can rewrite that as the square root of 16 times the square root of -1. Well, we know the square root of -1 is I, and we know the square root of 16 is 4. And so this solution would be 4I. Square root of -70. Square root of 70 and the square root of -1. Square root of 70, that's 10 times 7 and 2 times 5. So I can't actually simplify the square root of 70. So we'll leave that be. And we'll just say, all right, well, the square root of -1 is I, and we're leaving the square root of 70. And like we just said, if there's still a radical in my answer, the I goes in front. Every other time, the I goes in back. So let's try the square root of -48. We have the square root of 48 times the square root of -1. Square root of 48, let's see, we have 4 times 12, 4 times 3. Remember, square roots have two of the same number. So we have 2 4s, which means we can pull out a 4. The 3 gets left behind. So we're pulling out 4. The square root of -1 is I, and the 3 stayed under the radical. So 4I times the square root of 3. when you're working with negative radicals, it says use the definition that we talked about above before you do any other operations or rules with radicals. So that means always take out I first. Otherwise, we'll get different answers. So I would start here. That's I times the square root of 7 and I times the square root of 7. Multiply like terms. I times I is I squared. 7 times 7 is 49. The square root of 49 is 7. I squared is negative 1. Remember, this is multiplication here because they're right next to each other. So we really have 7 times negative 1, which is negative 7. Letter B. I times the square root of 6. I times the square root of 10. I times I is I squared. 6 times 10 is 60. So if we're simplifying, that's 2 times 5. I have a pair of 2's that can get pulled out, and 3 times 5 is left. And remember that I squared is negative 1 times this radical. So we have negative 1 times 2. The 2 got pulled out. And then 3 times 5 on the inside. Negative 1 times 2 is negative 2. And 3 times 5 is 15. Letter C. So I'm going to pull out the I and the I. Well, whenever we have the exact same thing on a numerator and a denominator, they reduce out. So our i's can reduce out. Because these are both radicals, we can say 20 divided by 2 under the square root is the square root of 10. Letter D, pulling out the I, the 48, the 24, we leave it. Because these are both radicals, we can say 48 divided by 24. 48 divided by 24 is 2. We cannot take the square root of 2, so we leave that alone, and that is I square root of 2. All right. We're rewriting this quotient. I'm going to start with that square root of negative 128. I'm going to pull that over here on the side. Again, pull out the negative 1 and the 128. From there, I'm going to reduce the 128. Looks like I can divide by 4. So that'll give me 32. 32 I can divide by 4, and that's 8. 8 is 4 times 2, and 4 is 2 times 2. So I have a pair of 4's and a pair of 2's with a 2 remaining. Remember, we multiply together everything that we pulled outside. So we have 2 times 4 times I, because we have the square root of negative 1 is I. And then we have the 2 left underneath there over 4. 2 times 4 times I is 8I. And then I look at the 8, 8, and 4. We don't look at the square root of 2 because remember the square root of 2 is different. It's not a like term. But the 8, 8, and 4, do they have a common factor? And they do. We can divide all of them by 4. So negative 8 divided by 4 is negative 2. 8 divided by 4 is 2. And then 4 divided by 4 is 1. So this is simplified form. Adding and subtracting. When we're adding and subtracting, this is just like when we were adding and subtracting polynomials. We're combining like terms. So we add or subtract the real parts and add or subtract the imaginary parts, aka like terms. So our like terms, we have 3 and negative 2, and then 4i and 6i. Don't forget, I always comes last, unless we have a radical. So 3 plus negative 2 is 1. Negative 4i plus 6i is positive 2i. And that's it. That's done. I can't do anything more with that. Letter B, I'm going to go ahead and do the keep, change stuff over here, taking the subtraction to the right. Our like terms then are negative 4 and negative 6, which make negative 10. 3i plus 7i is 10i. That's it. I can do nothing else because they are not like terms. Multiplication. So for multiplication, you can use any of our multiplication methods. You can FOIL, distribute, use the box method, but you should always get I squared in here. And then remember that I squared is equal to negative 1. So I'll start here on letter A. I'll distribute. 2 times 3 is 6. 2 times 4i is 8i. Negative 3i times 3 is negative 9i. Negative 3i times positive 4i is negative 12i squared. Now there's my I squared I was looking for. Want to always take that I squared and change it to the negative 1 that we know that it is. So this is really negative 12 times negative 1, which is positive 12. Now I can take a look at my like terms. These two are like terms because they both have I. And then the 6 and positive 12 are like terms because they don't. 6 plus 12 is 18. 8i minus 9i is negative 1i. And that's done. Letter B. Remember, we can never distribute a square when we have adding or subtracting on the inside. So this really means we have 4 plus 3i times 4 plus 3i. 4 times 4 is 16. 4 times 3i is 12i. 3i times 4 is 12i. And 3i times 3i is 9i squared. Now go ahead and take care of this 9i squared. That's really 9 times negative 1, which is negative 9. That means that these two I terms are like terms, and then the 16 and negative 9 are like terms. 16 minus 9 is 7. 12i plus 12i is 24i. And that's done. Letter C, 6 times 6 is 36. 6 times 5i is negative 30i. 5i times 6 is positive 30i. And negative 5i times 5i is negative 25i squared. I'm still taking care of this I squared first. So negative 25 times negative 1 is positive 25. That makes our like terms negative 30i plus 30i and 36 plus 25. Well, these 30 and negative 30 add to 0. So 36 plus 25 is 61, and we have 0 i's. So if they ask you to write it in standard form for complex numbers, you have to write that 0i. Otherwise, you can just write 61. Conjugates. I'm going to fill these in. We have real number and complex conjugate. So basically what it's saying is that, when we look at our polynomials that we were adding, subtracting, multiplying, dividing, factoring, they didn't have i's in them. And the reason why is because all i's come in pairs. If we had 3 plus 5i, the conjugate of that would be 3 minus 5i. If we had negative 2 minus 6i, the conjugate of that would be negative 2 plus 6i. If we had 4 minus 9i, then that would be 4 plus 9i. And so as you can see, the conjugates always only ever change the sign in between. And the reason why this happens is because when we multiply them together, we end up losing I. And so we just have a real number, which is why our polynomials only have real numbers listed. And so that's what we're going to work on in this section. Is we're going to use conjugates to simplify a format. Now we did adding, we did subtracting, we did multiplying. So this is part of our division. So we use conjugates of the denominator. And then just remember, because these are fractions, whatever you do to the top, do the same to the bottom, and vice versa. Of course, it's supposed to be whatever you do to the numerator, you do to the denominator, and vice versa, to use proper math terms. So we start with, what is the conjugate of 5 minus I? Well, the conjugate of 5 minus I is 5 plus I. So if I have 5 plus I on the bottom, I also have to multiply the top by 5 plus I. So now I have two multiplication problems. I'm going to start with the top and I'm distributing. So 3 times 5 is 15. 3 times I is 3I. 2I times 5 is 10I. And 2I times I is 2I squared. On the bottom, 5 times 5 is 25. 5 times I is 5I. Negative I times 5 is negative 5I. And negative I times positive I is negative I squared. I have an I squared on the top, so this end is really 2 times negative 1, which is negative 2. On the bottom, I squared is negative 1, so this is really minus negative 1, which becomes adding. On the bottom, these middle terms, 5i minus 5i, add to 0, and we have 25 plus 1 is 26. And there we are. There's where our conjugates eliminated the I, and now we have just a real number in that denominator. I know how many pieces 26 pieces of pie are. I can have that if I want it. I probably shouldn't, but I can have it, right? On the top, our like terms in the middle, 3i plus 10i is 13i, and then 15 minus 2 is 13. So we have 13 plus 13i over 26. Remember, this is technically a fraction, so we have to check to see, can I reduce it? So do 13, 13, and 26 have a common factor? And they do. I can divide everything by 13. So I have 1 plus I over 2. For letter B, we are multiplying by negative I. The opposite of a positive I is a negative I. We're taking this part from A. So 3 times negative I is negative 3I. I times negative I is negative I squared. We have no reducing to do to the negative 3I, but on the bottom, negative I squared is really negative negative 1, which is 1. And so that becomes just 3I. This is kind of a shortcut rule for simplifying if you have various other exponents of I besides just I and I squared. So we know that I to the first is I. We know I squared is negative 1. I to the third is really I squared times I. I squared is negative 1. I is I. Negative 1 times I is negative I. I to the fourth, I can break up into I squared times I squared. That's negative 1 times negative 1, which is 1. And then this pattern keeps repeating. I to the fifth is I to the fourth times I. We know I to the fourth is 1, and I is I, so 1 times I is I. I to the sixth is I to the fourth times I squared. I to the fourth is 1. I squared is negative 1, and so that's negative 1. I to the seventh is I to the fourth times I to the third. I to the fourth is 1. I to the third is negative I, and so that's negative I. I to the 8th is I to the 4th times I to the 4th, which is 1 times 1, or 1. And so you can see we have I, negative 1, negative 1, negative I, and 1, and 1. And that pattern just keeps going and going and going and going and going. So if you were asked to simplify something with that, that's how you could do it. All right, that is it for section 1.3. Have a great rest of your evening.